Okay, I started it. Thank you once again. And again, this is a problem, saltwater intrusion, that has to be studied by taking into account its variability in time. And we say that it's a non-stationary problem, and its variability in space. And the variability in space is taking place along the three directions of space. So actually, we say that it's a three-dimensional problem, a 3D problem. Actually, the independent variables are four: time plus the three directions of space. As usual, when we deal with these problems, which are highly complex, as usual, we try to simplify them, because within engineering, we also have the need to devise practical solutions. And therefore, very often we need to use robust approaches, which means that we simplify the problem and we study an analytical treatment with reference to a simplified configuration. The reason is that from a technical point of view, we don't really need a very detailed representation, because in any case, we have to deal with uncertainties. Uncertainties that are related to the description of the groundwater media, the description of the soil, the description of the forcing, because saltwater intrusion is also dominated by random forcing, which comes from the sea. And therefore, in view of the uncertainties that we have, in any case, we have to adopt safety factors when we pass to the design. We have to, in a way, introduce some allowance for this uncertainty. And therefore, it means that, a detailed representation is not very useful, because it looks like, for instance, if you took a picture with a very detailed camera with a lot of megapixels, and then you see your picture on a screen that has a low resolution. So it's not worth using a very detailed camera if you don't have a good resolution screen. The same for us. It's useless that we use the detailed representation if the data that we use for solving our problem are affected by a so relevant uncertainty. So we opt for a simplified solution, which makes the problem tractable on one end, and on the other end, it doesn't imply a loss of information with respect to the technical design. And let's look at this simplified solution. If you look at the lecture that I proposed to you, the lecture is also mentioning Darcy's law, because this is already a simplification of our problem. So a first simplification is to study the flow in a 1D setting by using Darcy's law. And this is, in a way, already a very important simplification. Darcy's law allows you to take into account the variability in time of the flow, because Darcy's law can be expressed as a function of time. On the other hand, it simplifies greatly the problem because it refers to a 1D problem. And we already discussed a little bit about Darcy's law. When we derived the groundwater flow equation, you may remember that at a certain point we decided to simplify the problem by introducing the Darcy's law, and which is conditioned by some assumptions. So I'm not repeating this treatment here, because what I want to make today is to go to a further simplified problem. So I want to introduce a further simplification, which is the simplification of referring to hydrostatic conditions. hydrostatic conditions means that I assume that the whole system is not changing in time. So I am studying a 1D problem with conditions that don't change in time. So I expect that the sea level doesn't change in time. I expect that any groundwater condition in the land, remember that groundwater in the land is opposing the intrusion of seawater. So I assume that also the groundwater condition in the land don't change in time. So there might be a flux of water from the land to the ocean, but I'm not interested in studying this flux. I'm just interested in studying the position of an interface between freshwater and saltwater, an interface that I assume static. Let me refer to a figure on the screen. So this is the condition, it's in French, but I think you can understand. I refer to, basically, I have, just let me open the image in another, here. I have a separation between salt water in dark blue and fresh water, which is light blue. I assume that there is a substratum, which is an impervious layer with no permeability, which is limiting the groundwater in the bottom. And I assume that there is a non-saturated zone in yellow close to the surface. So what happens here is that through the separation between land and ocean, you have, of course, an intrusion of salt water. And I assume that you see that the flow of the aquifer, or the flow of water can be in two directions. It may be saltwater intrusion if I have a level of the sea that is higher than the level of the water in the land. But I can also have a level of water in the land which is higher than the level of water in the sea, and therefore I have a flow of water from the land to the sea, but I'm not considering these changes. I refer to a static condition. So I'm not referring to a real situation where it may happen that I have a two-directional flow. I refer to a unique static condition. And this unique static condition, let me have a look at another figure. In order to study it, I also make another assumption. Let me see if I have another figure. Just 1 second. I'm just scrolling up. No, lower down. Sorry if I'm scrolling rapidly. I just need to find a figure to show to you. This one is fine, but it's too complicated. Okay. This is the figure I'm referring to. And so what I want to study is the position of this separation that you can see between the saltwater and the freshwater. And I assume, besides assuming that everything is static, I assume that there is no zone of dispersion. In this figure, you see that there is indicated a zone of dispersion. This is actually what happens in the reality. You don't have a sudden separation between saltwater and freshwater. You have a gradual decrease of the concentration of salt in the underground. But I assume instead that there is no zone of dispersion. I assume that there is a sudden separation. There is a surface which in my 1D problem becomes a line, a surface where suddenly I pass through from saltwater to freshwater. And let me see if I have other figures, like here. You see, if you refer to the left figure, you see there is saltwater on the right, freshwater on the left, and there is a sudden separation. Okay? And this is the situation which I refer to. this is a further simplification. It's not what actually happens in the reality, but you will see that by assuming static condition and sudden separation, I can easily study the problem. It becomes an equilibrium problem, as we will see. Okay, now let me go to a figure which is drawn by hand here. Look at the figure on the right. Let me just open it in another window. As I said, look at the figure on the right. You see that there is the land on the right with the fresh water. The fresh water is depicted here in blue, okay? And then I have the level of the land above, and between the level of the land and the level of fresh water, there is a white zone, which is unsaturated, okay? So what is important for me to solve this problem is to know the level of the water in the land, and this level of water is increasing as I move into the land. Why it's increasing? Because if I want to have a flow from the land to the sea, I need, and this is what happens in nature. In nature, it rains over the land and water flows from the land to the sea. But in order this to happen, I need to have an increasing level in terms of absolute altitude as I go into the land. Increasing level means increasing energy. It means that I have the fuel for pushing the water towards the ocean. If you look on the left of the right figure, you see the sea, and you see the sea level, which is assumed to be static, a constant level. I also assume that the level of fresh water in the land is constant. And then in the underground, I have a separation, a surface of separation, which in the 1D problem is a line. It's the line separating the gray zone of salt water with respect to the fresh water, which is depicted in blue. Now let me redraw this scheme on the blackboard because I want to make it very clear. And let me just look at the camera, which I have to rotate towards the blackboard. Okay, very good. So let me take chalks of different colors. So let me redraw this figure. So let me start from the level of the ground, which comes from the land and then goes down towards the bottom of the ocean. This is the level of the ground. So here I have the land, and here I have the sea. Sea, ocean, I use them as synonyms. Now let me indicate here the saltwater level, and I would like to get a chalk with a different color, but I have only a few of them. So let me take the blue to indicate the level of the sea. Okay, this is the level of the sea. Good. Now, let me use the green chalk to indicate the level of fresh water, which goes up into the land. Very good. Now, what happens in the underground? In the underground, you have water from the land that goes in the direction of the sea, but from the sea you have water that is pushing against the ground. So these two waters are fighting, and they are fighting in a way that it's not really they don't have equality of opportunities, because seawater has more power. Why? Because the weight is higher. What is the weight of seawater? With an average salinity, first of all, let me indicate W, it's my specific weight. For fresh water, what is the specific weight of fresh water? This is something that you have to be very clear in your memory. It may happen that the exam I ask you a question like this, like what is the weight of fresh water, specific weight? And of course, these are the questions that you don't have to fail, okay? And particularly at the exam, it's not a big trouble because, I mean, we always find a way to resolve. But when you speak with your clients, when you speak with the technicians that you have to coordinate, if you demonstrate, if you fail in basic questions, then you lose your credibility. So what is the specific weight of fresh water? Let me refer to the technical system. It's 1,000 kilogram forces per cubic meter. Okay, so 1 cubic meter of water weighs 1,000 kilograms. So another question may be, what is the weight of 1 liter of water? I don't give you the reply, but you have to know it, okay? Okay, now what is the specific weight of salt water? This is a more tricky question. It's higher. And with the average salinity of the sea is 124 kilogram forces per cubic meter. So you may say it's not a big difference. Actually, it's not negligible, okay? Because it's about 2%, which is, I mean, not so negligible, okay? Now, these two waters in the underground, they fight. And given that the salt water is heavier, basically, if they meet in the coastline, in this point here, you see, this is the coastline, okay? If they meet at the same level, which is what usually happens, because the equilibrium is such that they meet at the same level, as I depicted in this figure. So if they meet at the same altitude, given that salt water is heavier, salt water intrudes. It pushes fresh water into the land. So what I am expecting is a surface of separation which goes into the land. But then, as we get into the land, the level of fresh water increases. The altitude of fresh water, you see the green line, it goes up. And the reason why it goes up, I already explained it to you, because if it wouldn't go up, then if it didn't went up, then we would have an intrusion. We wouldn't have any groundwater flow, any freshwater flow from the land to the ocean, which is impossible. It's impossible because it rains over the mountains, and of course the groundwater in the mountains is higher than the groundwater, than the level of the sea. And therefore, if you go into the land, the green line has to go up. As the green line goes up, the freshwater gets more energy, and therefore it gets more strength to push the salt water back. So I am expecting that the separation between salt water and fresh water goes down. So I'm not expecting that salt water goes up intruding. This doesn't happen. Why? Because I have an increasing level of fresh water in the land that pushes groundwater down. This is what happens. the fresh water pushes salt water down. I repeat, the fresh water pushes salt water down. Why? Because the fresh water is gaining more strength for its increasing altitude. So what I expect is that for increasing altitude of fresh water, I get more strength to push salt water down, and salt water goes down. Of course, this reasoning is based on equilibrium between forces, equilibrium between energies, and is then based on two assumptions. First, that I don't have any time variability in this system. So the level of fresh water and salt water, it's not varying. Of course, taking into account time variability makes the problem more complicated, because this equilibrium would continuously change. So this is the first assumption, which I can call in this way: hydrostatic condition. And then there is the second assumption. I hope that you can see, let me see, the bottom of the blackboard. Yes, you can see it. And then there is the second assumption, no dispersion. So the separation is aligned. In 1D is aligned. Okay? Now, at this stage, what is my technical problem? My technical problem is precisely to locate the position of this surface of separation, of this line in my representation. Oops. Okay, now, how to locate the surface of separation? I just have to study an equilibrium of weight. Basically, what I have to impose is that on any point lying on this line, and for instance, let me identify this point here. On any point of this line, I have to impose that the weight of fresh water, let me use the green, the pressure, and therefore the weight of fresh water is equivalent to the weight of salt water. Salt water is pushing up, fresh water is pushing down. Remember that pressure is isotropic, so the pressure that you have and therefore the weight of water that you have in a given direction is the same pressure in all directions. So what I have to estimate for this point here is the weight of salt water, which is given by the salt water that is above this point. And the salt water is indeed above this point, because if you see the sea level is higher than this point that I have considered, that I am considering here. So there is a weight of salt water that pushes this point up. Imagine if you remove fresh water from here, what happens to this particle of water that is placed here? If you remove fresh water, there is the weight of salt water that pushes this particle up. And why? Because I have some salt water that is placed above that weights, and through the weight gives pressure. Okay? Now, the same thing for fresh water. I have fresh water above this point, which has a weight. It pushes this particle down. I just have to compute these two weights. And let me refer to the figure that you see here on the left. Now, so on the left, here it's a simplified scheme, but the problem is precisely the same. What do you see on the left? You see that you have salt water or saline water in gray, and let's suppose that this U is a U pipe, okay? The U is a pipe. If you put fresh water in the left channel, what happens? Imagine that these two vertical segments are indeed vertical, okay? So this pipe, this U, is placed with it alongs in the vertical direction, okay? So this is the H is measured, the capital H and this in the lowercase h on the right are measured along the vertical direction. So if you put and if you imagine that there is a surface of separation between salt water on the left and fresh water, which is depicted on the right in blue, if you imagine that there is a surface of separation that is without any dispersion, then what you have to do is precisely to estimate the equilibrium in the surface of separation. If you look at my mouse, it's moving on the surface of separation. And you see that the level of fresh water needs to be higher in order to keep this equilibrium, because fresh water has less weight. So what we have to do here is to compute the weight of the salt water above the surface of separation and equate it to the weight of the fresh water above the surface of separation. So let me refer to this figure and let me write this equilibrium on the blackboard. I hope I am using the same symbols. Let me just look at the web page because I want to use on the blackboard the same symbols. Just 1 second, I look here. Okay, gamma S, gamma salt, gamma F. Okay, very good. Very good. Okay. So, let me refer to the figure that you see on the screen. And let me write then the equilibrium condition. So the weight of salt water, gamma S. Gamma S is the specific weight of salt water. If I multiply gamma S through capital H by capital H is the level of salt water above the surface of separation. What I get is the pressure of salt water on the surface of separation. I write here pressure of salt water Okay, this is the pressure of salt water on the surface of separation. Okay, now, if I want to reach equilibrium, the pressure, which is equivalent to the weight, the pressure is a weight for unit area. So the pressure of salt water above the surface of separation, it's equivalent to the pressure of fresh water, which is given by gamma F, specific weight of fresh water, times HF, lowercase hf. And this is the pressure of fresh water. Good. I can rewrite this equation in this way. Gamma S times H is equal to gamma F times H plus, the symbol is lowercase h here. What is lowercase h? Is the altitude of fresh water into the land with respect to the sea level. Okay, very good. Now I can rewrite it in this way. Gamma S times H is equal to gamma F times H plus gamma F times lowercase h. I just multiplied gamma F by the two addendum inside the round parenthesis. Okay, good. Now let me write in the top of the blackboard. Look, what is the variable I'm interested in here? The variable I'm interested in is capital H. And you may ask why? Why are you interested in capital H? Because look now on the screen at the right picture. What I am doing here is for each point of the line of separation between fresh water and salt water, I am studying the equilibrium for each point. So, if you look at the figure here, now I'm studying the equilibrium for the point where my mouse is placed. And then, for each point of this line, I am interested in knowing the depth with respect to the sea level of this point. Okay, and let me, give me 1 second. I want to see if I have any. Okay, let me take this figure and let me copy here on this graphic blackboard because I wanna. Very good, just 1 second. Okay, now let me use, okay, let me take, very good. Let me see if it works. This, yeah, it works, but I would like to use, okay, this. Just 1 second because I heard, okay. I heard a ring I had to admit your colleague. Okay, very good. Now, what I am doing on the blackboard is to study the equilibrium of this point here. Okay, this is precisely what I'm studying, the equilibrium of this point. And therefore, I am interested in knowing, as I said, H. Why? Because H is precisely the position of the separation line for this point. And of course, then I will have to study the same equilibrium for another point, for instance, this one. Okay? And then for a subsequent one, for instance, this one here. And then maybe also for this one here. I need to study the equilibrium for all the points of the separation line. But of course, once I understood how to make it for one point, it's very easy to make it for the other points. And if I have time, I will also propose to you an exercise in R. You will see that it's extremely easy. Now, keep just in mind that we are interested in knowing capital H. So let's go back to the blackboard. And by using this relationship here, let's find an explicit representation for capital H. So let me put the terms with capital H on the left-hand side. And therefore, I can write capital H, which multiplies gamma S minus gamma F. This is equal to gamma F times H, lowercase h. Very good. Now it's very easy. Capital H is equal to, let me take some space, some room on the blackboard. Capital H is equal to gamma F lowercase h divided by gamma S minus gamma F. Okay, good. Now, this is more or less equal to gamma freshwater is 1000 H, and at the denominator we have 124 minus 1000, it's about 25, or let me put 24, okay, and this is equal. And this is more or less 40 lowercase h. Let me write here the conclusion. Capital H is more or less 40 lowercase h. You see that the conclusion is very easy. The conclusion is very easy, but it's also a little bit astonishing. A little bit astonishing because, you know, let me just rewrite what you see on the screen, okay? What you see on the screen, namely our sketch of what happens in the underground. So here we have our ground with the sea level here, and we have the fresh water here, okay? And basically, this is my, let's suppose that I want to go study the equilibrium along this vertical line. Okay, this is my lowercase h, and I am interested in knowing let's suppose that the equilibrium is here. I am interested in knowing this uppercase H. Now, you see that this formula tells me that uppercase H, which is the depth of salt water, is about 40 times the depth of fresh water above the sea level. Okay? And then, of course, I have to take another vertical. And the other vertical may be here. Okay? And here, I have a lowercase h, which is lower, which means that uppercase h, the depth of salt water is lower as well, but with a multiplying factor of 40, which means that a small change on the level of fresh water implies a big change in the depth of salt water, which means that if with a human intervention you reduce lowercase h, which is again the groundwater level. So if you take water from a well and you reduce of, for instance, 1 unit the groundwater level, then you have salt water coming up for 40 units. So the effect in terms of saltwater intrusion is amplified by a factor of 40, which means that indeed we have to be very careful with the groundwater level and saltwater intrusion in general. Why? I said 1 week ago, I said, look, 15 centimeters of sea level increase are not much in terms of coastal flooding, but they are very important in terms of saltwater intrusion. And the reason is that, you see, there's amplification of effects, and which, I mean, it is something that we need to consider. Of course, here we have some simplifying assumptions. This is static, and also we assumed no dispersion. And this simplifying assumption basically imply a higher risk in the reality, because, you know, we are assuming a constant seawater level. Let's suppose that you have a storm, and therefore, which means that you have a very relevant energy coming from the sea with the waves. These waves are pushing salt water into the land, which means that indeed you may have a contamination by salt water of the underground. And then, even if when the storm passes, you have fresh water again coming back, pushing back the salt water into the ocean, but meanwhile you get some salt in your wells, in your underground, and it takes a long time to recover. So the fact that the system is not static, the fact that during storms we have an higher sea level is something that increases the risk with respect to the static condition. And this is one thing. And also the fact that you don't have a sudden separation between salt water and fresh water, but you have a dispersion zone, this increases your risk. And therefore, it is something that you have to carefully consider, saltwater intrusion. Okay, let me see if there are any questions in the chat. Do you have any question, by the way, so far? Okay. So let me now close this graphic blackboard and let me go back to the web page to see if I forgot something. I wouldn't say that. Now, what are the factors that affect the saltwater-freshwater interface? We already made a short description of these factors. I want to call them back because now that you understood better the dynamics of the process, you can look at these drivers with different eyes. And also, I want to set the basis with some considerations on the solutions. Because, of course, very often when we are called to study saltwater intrusion is because there is a problem. And the problem is the fact that, for instance, people found increasing salinity in their tap water, which means increased salinity in the wells. And therefore, you have to find solutions. And finding solutions, of course, once that the problem is already there, it's not easy. And in order to find a solution, we have to know the causes. Remember, if you want to solve a problem, you have to know, first of all, the causes of the problem. So, what are the factors? Rising sea level, okay, and also keep in mind that sea level rise may be caused by land subsidence, which is a relative sea level rise, and there might be a change in precipitation, because change in precipitation means less infiltration and means less strength for groundwater. If you decrease the amount of groundwater, you, of course, increase your chances of getting saltwater intrusion. And there might be reduced infiltration for soil compaction or soil drainage. Today, we tend to improve our drainage efficiency for the land and for the roads, for the cities. But improving drainage efficiency means that we have reduced infiltration, and therefore we have less groundwater. There might be increased evapotranspiration, which may be caused by the heat island effect, may be caused by a change in agricultural production, may be caused by climate change. And so basically what may happen is what you see in this figure that now we can comment with full understanding. If you look on the left, you have the natural situation. If you look on the right, there is the situation that might be originated by pumping, by excessive pumping, which means that you have so the central figure is depicting actually the sea level rise, which may push salt water into the well. And the right figure is the effect of overdrawing, which means overexploiting groundwater. Again, you may have the intrusion of salt into the well. This is what, of course, we are concerned of. Why are we concerned by sea level rise? Because we can't use the wells anymore. And the same is shown in this figure, where you see the same issue. Basically, you may have saltwater intrusion for overpumping, but it also shows that the saltwater intrusion may happen through surface water, meaning that if you get rivers that flow into the sea getting salted, and the reason may be that you reduce the river flow for some reason, of course, you may get the salt water intruding into the rivers and from the rivers infiltrating into the ground. And this is something that happens frequently because major rivers are often dammed in order to keep some of the water for civil use. For instance, if you consider the Colorado River, if you consider the Danube River, all of these big rivers are dammed also along their course, because the idea is to store water during the river reach in order to use this water in the dry season for irrigation, for civil water use. An exception is the Po River. The Po River is in its lower course. It has only one dam. In fact, there was a project some years ago to increase the number of dams along the Po River in order to, as I said, save water, store water along the river reach. But actually, if you decrease the flow of the rivers, what happens is that at the interface in the estuary, in the delta, between freshwater and saltwater, you may have intrusion of salt. And if the river gets salted, it's a problem, because then there is a salt contamination also into the land. And this is what is shown in this figure. So, in order to detect the problem, it is essential to monitor salinity. And I want to give you an example, which is the monitoring network, which is placed along the Po River delta in order to measure the salinity. And let me just open the figure in another here. You see the map of the stations. These symbols that you see, the symbols are similar to the euro symbol, with the numbers identify monitoring stations. And this monitoring station, you see that there are some monitoring stations in the sea. And in order to get a baseline information, salinity into the sea, and then you have monitoring stations along the river reaches, because what we expect to see is a decrease of salinity along the river, and a reduction of salinity into the land at a certain distance. And we have to monitor that the salinity into the river is more or less constant and doesn't increase. And this monitoring here, it is shown only the monitoring along the rivers, but there are also monitoring stations in the wells, because we have to monitor, we have to make a combined monitoring of rivers and wells. And this is the way we monitor salinity. Now, let's discuss a little bit about the solutions. And this is a figure that depicts the progress of salinity. Let me open it here. The progress of salinity along the Po River has detected in the day August 9, 2012. Its monitoring in summer is extremely important, because of course in summer you have the lower levels of groundwater and the lower levels of flow into the rivers. And you see that from the dark blue to the very light blue, you get a decrease of salinity, and also to the green. And you see the scale. Unfortunately, it's in Italian, but it's easily understandable. You see the scales of the levels of salinity. And of course, in the monitoring network, you have also warning levels that allow you to make decisions. And to make decision means to adopt strategies for contrasting saltwater intrusion. Now, let's see what are these possible actions. So, we may define them classify them in three categories. The first category of actions is modification of groundwater and surface water withdrawals. Of course, we have seen that overexploitation of groundwater and also fresh water, because we discussed also damming. Overexploitation is one of the causes of saltwater intrusion. So a first category of solution is to reduce these withdrawals. We have a second category of solutions, which is modification of groundwater and surface water deliveries, which means that we can increase the flow, we can increase infiltration in order to replenish groundwater, or we can we can increase the river flow in order to, of course, give more strength, more weight to fresh water. A third category of solution is using engineered structures like sheet piles, for instance. Of course, if you create in the proximity of the coastline an impermeable layer, then you don't have any more saltwater intrusion. Saltwater intrusion takes place if there is a sufficient permeability in the underground. And so another option is using engineered structures. We are not going into the details of designing these solutions, but I want to give you an overview. And I think this table is an excellent summary, along with references of strategies, approaches, and tools to mitigate the impact of saltwater intrusion in coastal regions. And here you have also the references, which may help you in the future if you have the need to design a strategy for limiting saltwater intrusion. So basically, you see the three categories: modified water withdrawals on the left column, modified water deliveries, and engineered structures. And you see the approach that you have to follow, which means that for modified water withdrawals, you have to optimize this, the water supply for irrigation in particular, because we know that irrigation is it's the most important component of freshwater consumption. And therefore, if you adopt precise irrigation, if you reduce the water losses, of course, you optimize water delivery and reduce water withdrawals. And what the tool that you need is modeling and scenario analysis. And you see the references. Modified water deliveries, you may adopt water conservation. And water conservation is another approach that falls into the strategy of modified water withdrawals. Water conservation here basically talks about irrigation efficiency because it's the most important component, but also we can also talk about water losses here. And there is also rainwater harvesting, which is another way of modifying water withdrawal. Rainwater harvesting means that you collect rainwater and use it for irrigation for the purposes that are allowed. Now, modified water deliveries. Basically, what we have to do is enhance groundwater recharge is a solution, and manage the river flow in the surface water. Here it's not mentioned. Do you have any question? Because I see a micro open. And again, we have modeling and scenario analysis as a possible tool. Just a second, because I need to. Can you please close the micro? Thank you. 1 second. Okay, I'm sorry, I needed to close the micro. And then there is the use of infiltration ponds, basins, land use conversion, artificial recharge. Artificial recharge is frequently used. It is the opposite of water withdrawal from wells. Instead of getting water from the wells, you artificially recharge them. And then the engineering structures, and you may consider diversions, which means that you divert the water flow of rivers in order to increase the flow of selected rivers, and also to impede salt water is another possible approach, which means that you may use saltwater barriers and other structures. Okay, I think that for what concerns this discussion, we are done, which is the last, let's say, part of the theory of this subject. Now we have some little bit more than 1 hour to go, and I would like to take this approach because I think it may be useful in order to consolidate your knowledge of this topic. Is we developed an exercise, but I would like to keep the exercise as the last issue, because before the exercise, I think it is priority that we make a recap and discuss a little bit about your exam. My proposal, given the timing, I would say that it's not useful if we start now and then make the break, the discussion. I propose to make the break now, 15 minutes, and then we meet again at 10:45, discuss the exam, and possibly, if we have time, the exercise. Do you have any question, any comment on this plan? Okay, very good. So let's take a break and let's meet again in 15 minutes. Thank you very much. Thank you. See you in 15 minutes. Yeah. Okay, students, here I am. So, let me trying to give you some information. First of all, let me make a recap of the course, as I said, and I share the screen again. So this is the list of the lectures that we discussed together, and just 1 second. Okay. Okay, good. So let's start from because the first 2 lectures are just nothing relevant for the exam. Okay, so the first, which is the learning process adopted in the course and the sustainability in the 21st century. This is something that has it's not relevant for the exam. It doesn't imply that it's not relevant for you. Of course, it's highly relevant. On the other hand, it's an information that I provided to you just for your personal information and your personal knowledge. But it's very descriptive, so it's not something that I ask at the exam. Keep in mind that at the exam, usually I make a limited use of descriptive questions. I focus on the technical details. Now, also, for what concerns the 3rd lecture, Sustainable Management of Water Resources, here, what's important for you to remember for the exam is the orders of magnitude. So I'm focusing on this figure, which gives a snapshot of the water volumes available on the Earth and divided by, for instance, salt water, fresh water, etc. Try to remember the orders of magnitude. So it's important that you remember that about 97% of the total global water is salt water, only 3% is fresh water. And it's important that you remember that groundwater is about 1/3 of this 3%. So just in order to get an idea of the distribution of fresh water, which is something we are concerned of. And also here you see this figure, which is the distribution of precipitation. What's important here is remember the orders of magnitude, which means, for instance, that you should remember that the global precipitation on average in 1 year is about a little bit less than 1 meter. You should remember that the precipitation in Italy on average is about 800 millimeters. These orders of magnitude are extremely important. They may be asked at the exam, okay? And climate classification is not something that I ask at the exam. And also all these numbers that follow, it's something that I don't specifically ask because you know they are too detailed. So these figures, which I think are extremely important to give you some information, they are too detailed in order to be, in my opinion, to be asked at the exam. So just try to remember the orders of magnitude that I specified to you. A question may be, what is seasonality? Why seasonality is important? Remember that in this lecture we said that overall there is enough fresh water on the Earth, even for an increasing world population. The problem is the distribution, which is uneven in time and space. Uneven in time means seasonality, uneven in space means geographical distribution of water. And please remember basic things like that most of the rain falls in the proximity of the equator in the tropical areas, and therefore where you have a lot of rain, of course, there is abundance of fresh water. So just try to get ready to describe at the exam possibly what is the distribution of fresh water in the earth in very qualitative terms, okay? And I think that's it. Because these costs, I don't think this is something that you have to remember. And here, groundwater, variability, these are things that are not asked at the exam usually. Okay, and then let's talk about the next one, inductive methods. This is a very, the subject of many questions at the exam. And a typical question is, what does it mean inductive assessment, deductive assessment? What is river discharge? Provide a definition. So volume of water through a given cross-section per unit time. And remember also flow duration curve, how to estimate the flow duration curve. What is a flow duration curve? How would you define it? How to estimate a flow duration curve? This is something that is very frequently asked. There are two methods, as you remember. One that pulls all the data together, the other one that estimates a flow duration curve per each year. Okay. And 1 second. Give me 1 second. I still have a student waiting. Okay. Okay, so flow duration curve is very important, and to this range, median annual flow duration curve, percentile, etc., these things that we discussed can be asked at the exam, okay? And also how to estimate the volume of water withdrawal, and how to compute the water withdrawal index and the water use index. These are also important issues that can be asked. This example of a run-of-the-river hydropower plant is not a subject for the exam, and I think groundwater is, we will discuss later. Okay. Now, deductive assessment. There are two important questions that I frequently ask, which are rainfall runoff models, so linear reservoir and IMOD, and also the rational formula. This is a typical question. What is the rational formula? You should be able to explain it, and also the assumptions, and try to remember at least the most important one. And the linear reservoir with the mathematical development, the IMOD model with the mathematical development. Okay, these are questions that often come up. IMOD is here. And then there is groundwater flow equation. This is something that may be asked. So how to derive the groundwater flow equation, and then you have to remember this mathematical development. Okay. I am scrolling down for, okay, and that's it. Now, model calibration and validation. A typical question is, what are model calibration and validation? And remember, you have to remember not only calibration, also validation, because I don't know why, but students usually are very good in explaining what calibration is, and they fail in explaining what validation is. So they are good for calibration, they are not good for validation. Remember also to study validation and the objective functions. This is something that is frequently asked. Also, you have to describe what is calibration, trial and error calibration, calibration through expert knowledge, and validation, as I said. Okay, now. Design of river barrages, a usual question is, can you please write down a sketch of a river barrage and describe to me what are the components, the most important components? And also for the river barrage, a question that is frequently asked is how to displace the different thresholds, the different weirs in terms of their height, in terms of their elevation, okay? And to answer to this question, you have to explain, you have to use these two relationships that you see on the screen now. These are, again, for determining the elevation of the environmental flow spillway, main spillway, and diversion or withdrawal spillway. You should also say something on the design of gravel and sand traps. This is another typical question, not the Stokes formula. So just give the Stokes formula for known, and then everything else, which is the sizing of the length of the sand trap and the sizing of the gravel trap, which we said it's usually done by using an heuristic approach. This is something that I frequently ask. And also the design of the head tank with the submergence of the pipe for delivering water downstream. And another typical question is the Blig-Lane relationship for checking against piping. And what are the solutions to avoid piping? And another thing that I may ask is how to shape the profile, downstream profile of the main spillway if we don't want to use the vertical wall. And you don't have to remember the formula of the Krieger spillway. You just have to mention that there is an empirical formula proposed by Krieger and Shimemi, which allows you to accompany the river flow downstream, okay? The current downstream. Okay, very good. Now, climate change and water resources, nothing to learn for the exam, but don't discard it because for your personal knowledge is extremely important. Assessment of human impact is something that I may ask. How would you assess the human impact on water resources? And decision theory. Decision theory, yes. Everything we discussed, it's maybe asked in particular how pairwise comparison works. And what's the difference between a top-down approach and a bottom-up approach, and how pairwise comparison works. So analytic hierarchy process and the computation of the matrix of the pairwise comparison, and how to check that the matrix is efficient. Of course, you don't have to remember this table, but you have to remember, for instance, also how to compute the consistency index and the consistency ratio here. And then there is saltwater intrusion, what we did today. This is something that I can also ask, how to determine the surface of separation in the underground between saltwater and freshwater. And what are the drivers of saltwater intrusion, human-induced, and the natural drivers? These are the typical questions that I ask. And what are the possible solutions? So cutoffs, sheet piles, or reducing water withdrawals, or enhancing infiltration, etc. This is the panorama of the possible questions. There is no question on the exercises. So this is something that I think, as I told you, it's extremely important, but there will be no questions on that. And now some information, and if you have any question related to the exam, please step in, and feel free also to ask me by email or the chat on Teams. So first of all, you have already your 3 dates for the summer, for June and July. It's already possible to book for them. Please debook if you change your mind. I need when the subscriptions close, I need to know the number of persons participating at the exam. And I will also fix a date for September, and so you will have an additional opportunity in September and an additional opportunity later on if you ask me. So in September there is no need to ask. Just remind me if you don't see any date in August. Please remind me. But I think I should be able to fix the exam in September before then August. What I need to know is the calendar of my lectures and the calendar of some other commitments that I may have. So I cannot fix the dates now, but I think I'll be able to make it in July. If by the end of July you don't see any date in September, please remind me, and I may give you some information. You can send an email. And after September, if you will need, I guess that most of you will have already taken your exam. But if you are still pending after September, you may ask me, I can fix additional dates in October and November. Actually, I couldn't, because the university recommends not to make exams during the lecture period, but I think I can make an exception. But I hope that, as I said, most of you have already taken your exam by the end of September. Now, what if you decline your mark? Of course, at the end of the exam, I may propose a mark to you. Not I may, I will propose a mark to you. Remember what I said at the beginning of the course. It's also recorded in the video. Usually, my evaluations are a little bit stricter than what the student expects. So it happens quite frequently that students are not happy with the mark. Usually I give a percentage of laude, which is about 5% of the participants, which means you are 15, 20, and 5% means 1. And also the number of full marks is sometimes lower than what the student expects. So I give you some suggestions. First of all, try to come at the exam well prepared, because if you want to get the full mark, you don't have to make any mistake, and you cannot skip any topic in your preparation. And so please try to follow this advice. Of course, you will be allowed to decline the mark that is proposed to you. If you decline, and let's try to decline just once. So my policy is that there is no problem to decline once. And for the second time, let's take an agreement. Okay, so if you decline once, then let's discuss about what may happen at the second time, because I'm not sure I can give the opportunity to decline more than one. Okay, but for the first time, you can decline. And if you decline, you can take the exam at the next round. So there are 2 dates in June. It's fine if you decline at the first date and you take the exam at the second date or the third one. It's not a problem. You just have one opportunity to decline, and then you can take the exam whenever you want. My suggestion, usually, if you are not happy with a mark, it means that you have to study more. So just think twice before repeating the exam after a couple of weeks, because in a couple of weeks, I mean, it's only a marginal improvement, in my opinion, is possible. But in any case, it's your choice. So I don't have any further recommendation to give. And I think that's it. Do you have any question? The exam is oral, as I told you, and it will take about half an hour. And for the numbers of students that I have in this course, usually it doesn't happen that the exam is overcrowded. So whatever the number is, usually I'm able to finish by the morning or maybe a first part of the afternoon. Do you have any question on the exam?
I do not have a question, but I have to highlight you a problem. On your YouTube page, there is one lecture missing, the one of the 4th of March.
Yes, that's true. And it was not recorded for a technical problem.
No, because we can see it in Teams, but not on your YouTube page. I don't know why. I wanted to mention it to you.
Okay, thank you. But so you see that in Teams it's available and it's fully available. You tried to look at it?
Yes.
Okay, let me see if I can see it.
It's present on the chat and also on Microsoft Stream.
Just a second. And I thought it was completely missing, so this is a good news. Just 1 second. 4th of March, you said, correct?
Yes.
Just 1 second. 4th of March, let me see. Okay, so it looks like, okay, 2 hours, 6 minutes. Okay, that's perfect. Okay, thank you very much. I will upload it in the YouTube list then. And
it's not a problem for us because we can see it anyway. But if you wanted to make it public for everyone, I wanted to.
Yeah. This is perfect. Thank you very much because I thought it was missing. Probably I made something. Okay, perfect. Probably I made some confusion. Okay, thank you. I will do it when I get back in my office because I can't do it here. Okay. Thank you very much. And any other question? Okay, good. So now
I would like to ask you if there are any problem with the preparation of the exam, if you are available on making, I don't know, a team call or something to answer any question that would come up during the preparation.
Yeah, this is a good question. Yes, I am available. Okay. And I am available also for individual clarifications or better collective clarifications. So what I suggest to you is if you would like to get any clarification, please do send to me an email. And then I can make an appointment for a Teams conversation, which I will extend unless you ask differently to me, unless you ask for confidentiality, I will extend it to all students. So I think I would like to wait for your request for this, okay? Because I don't want to unduly take your time. So if there is at least one request, I will do it. Otherwise, but I would prefer to wait for your input, if you agree, okay? And
okay, thank you.
Just use the email or the Teams chat. It's no problem. Okay, perfect. Any other question? These were very relevant questions, so thank you very much. Any other question? Okay, good. And now, let me think if, okay, I forgot to say one important thing actually for the exam. The exam will be possible in both physical presence and online. And I will be very empirical and practical, meaning that you subscribe to your exam, which is fine. And then I will send you an email during the previous week to all the people who subscribed, and I will ask you whether you want to take the exam in physical presence or online. And so the exam day, those people who are booked in physical presence will be done maybe at the beginning in the library of my institute, which is Costruzioni Idrauliche. So the room will be in Via del Risorgimento, and those who will be attending online, I will call them after completing the exam in physical presence, and I will make the exam one by one. There is no difference. So it's an oral examination. The duration is the same. I would appreciate if you take it online, if you could use a camera that allows me to see what you are writing, because I will anyway ask you to write down something. And so if you have a camera that can be oriented in order to look at your table, it's much better. But it's not a strict requirement. I can adapt, even if the camera is not looking at the sheet. I think it's much better for you. So this is why I take the liberty of advising you, because I think you feel more comfortable if it's a more direct, otherwise you have to take the sheet, put the sheet in front of the camera after writing, and it becomes a little bit messy, but still, it's no problem, just an advice that I give to you. I have no preference, so to me it doesn't matter. You can take the exam online or in physical presence. It's really no preference from me. I know that some students really would like to get it in physical presence, so this is why I'm making myself available. And please bear with me, because of course, by combining the two solutions in the same day, it's a little bit more time-taking, but so you need to be more patient. But anyway, it's not a big problem. Okay, so my suggestion now is, given that we have about half an hour, I would like to take this time to look with you at the exercise, which I think it is helpful in order to better understand saltwater intrusion, and it's also helpful to learn something more about R. Now, as you know, I can't use RStudio in this PC, so give me 2 seconds I hope that it allows me to connect, because last time it didn't allow me for some reason. I need to connect to my PC, and let me just 1 second. I need to de-share, because I think this is one of the reasons why it didn't allow me to connect, possible reasons. So it doesn't take much time, so I think it will take to us less than half an hour. Just 1 second, because I think I have the same problem, but anyway, for some reason from this PC doesn't connect. These are the mysteries of Windows. Let me just check. Okay, let's use the R console without RStudio. So you have to be patient a little bit, but it's not a big problem. Just 1 second. I open the R console, and let me just change the font. Okay, this is the R console, but you don't see it yet. Just 1 second. I need to share the screen. Okay, this is my R console. I clear the screen with Ctrl L. And then let's look at the website. What I am explaining now is related to an exercise, so it's nothing to do with the exam, okay? But I suggest that you are patient for some 20 minutes. And just 1 second, I go to my website. Okay, tutorials. And here you see that today I put this link, assessment of saltwater intrusion into the land. And let's look at the text. It says, it gives the coordinates of a cross-shore profile of seabed and land. What does it mean, cross-shore? It means that it's the profile of the land that goes in the direction from the sea to the land. It is crossing the shore. So this is why it's called cross-shore profile. So basically, if you look at the blackboard, just 1 second, I need to change the camera to here, to the other one. Yeah. So the cross-shore profile, it is this one. I am highlighting it with the blue. And so what you see in the PDF are the coordinates of this profile, which is seabed and land surface. And the coordinates are here, x, y. And then it gives the altitude of the sea level, and it gives also the profile of the fresh water level in the same direction cross shore. And the exercise is very simple. By assuming that the mass density of seawater and fresh water is 1024 and 1000 cubic meters, kilogram per cubic meters, the students is required to draw on the cross-shore profile the line of separation between saltwater and fresh water. Okay, good. This is exactly what we did in theory. Let me close this because I don't need this PDF anymore. And now let's look at the data file. This is the data file. It gives just the two profiles that are given in the PDF, okay? So very simple. This data file, however, should be saved in the working directory of R. So let's save this data file. I can click with the right mouse, and I save it in my desktop. Okay, save. Very good. Now, let's open the suggested R code. Okay, this R code should be put into R now. And basically, if you put it into R, through RStudio, it's the best solution. I can't use it. And in RStudio, you have to open a script and cut and paste this code into the script, okay? This code is self-explaining, but I just would like to go with you through it, and you see it's very short. Before going through it, let me go to the R console, and let me see what is the working directory, because I need to change it. And let me see if it's possible. I don't think here it's possible to. Okay, let me just see. Give me 2 seconds. I want to see what is the working directory now. It's this doesn't give me. Okay, let me. Dear. Just 1 second. I think I need. Give me 1 second, because I need, in the SAR console, I need to change the directory, which is very easy for you in RStudio. I need to set up the desktop as a directory, working directory, and okay. Okay, now. What this gives. Okay. Second. 1 second, because I need to. Okay. Okay. I found the comment. Just 1 second. Check it. Get WD. Okay, very good. So I think at this stage I just need to. Okay, I have to put the data file inside documents. So let me go here. I go back and save my data file in the document directory. So data file, save link as. Okay, and now I should get it. Data salt intrusion. Save. Okay, should be fine. Now, let me get the R code, and just to give you an example of how it works, what I get at the end, let me just select all. I select all, and I paste all. Okay, so I'm just selecting the whole file, and I copy it, and I paste it in the R console. Here it is. And let me see, because there is an error. which I don't see. No, this is fine. No error, but I don't see. Okay, let's try to, yeah. 1 second, because I needed a, okay, here, let's look at the graphic window. You see that I got precisely what I wanted to get. You see the profile of the land, which is the continuous black line. You see the sea level, which is the red line, which is also continued in the land, has a dashed red line. There is the blue line, which is the level of fresh water into the land, and there is the orange line, which is the surface of separation that I was requested to compute. So this is just to show you that everything works. Now, what I would like to do is to go with you through the code and try to understand what's going on. First of all, there are 2 instructions that aim to upload into R the data. And this is the first one. And then the data are put into an array. You see Badland is equal to array here. Let me see if I could. Okay, now it's better. The mouse. They are put into an array, and then they are put into the X and Y coordinates. And then for the freshwater profile, I do the same thing here. So these 2 groups of instructions just serve the purpose of putting into a matrix the coordinates of X and Y of the bedland and the freshwater. And then there is a remove of the temporary files because I don't need anymore the 2 matrices, because I already have put the coordinates into vectors named with X and Y for both freshwater and bedland. And now I can draw the plot of the bedland and freshwater. And you see that here there are 2 instructions which serve to display the line of the sea level. And it is a continuous line for the sea level from the side of the sea, and a dashed line. This option LTY equal to means dashed for the sea level into the land. So basically, if you cut and paste everything so far, you get the picture, and I go to the R console. Just 1 second. Not anymore. Let me close it. If you cut and paste, 1 second, because okay. Oh, here I am. Let me go to the console again. As I said, if you cut and paste this instruction up to this point, you get here the profile of freshwater, land, and the sea level. And what I did is, as I said, to cut and paste up to here. Now, let's look at the computation, first, which is very, very quick, as you see. First of all, there is a smoothing of the freshwater surface. So I want to smooth it. I want to make it more regular. And these are 2 instructions that just are finalized to smooth the freshwater surface. And just look at the help for these two instructions. But basically, the first one, this one, allows you to transform your freshwater profile into a vector which is longer. You see that basically it's a vector that counts 80 coordinates here. And the reason is that I want to increase the resolution. So what I inputted into R is a profile that has a low resolution. I want to increase its resolution, and the increase is done through this instruction, which does a linear interpolation of coordinates. And then with the second instruction, I am smoothing the surface. So basically, what I get up to here is, just 1 second, let me look at the console. And 1 second. It's already computed. So let me just do, because I want to start from the beginning. So, just 1 second. I want to start again in order to show you what is the result of each single step. 1 second. Okay, so I have to remove everything, H, PR1, okay, X, deadland, X. Let me remove all the variables. Okay, now I removed everything. Okay, let me see. Okay, it's clean, and let me just copy the file from the beginning to up to here. Okay. Okay, now if you look at the plot, which is, but before, okay, let's look at the plot. Just 1 second. Okay, now let's look at the plot now. Okay, this is the bedland. Look at the plot window, and then let me get the lines. This is the line of fresh water, and this is the line of the sea level, and this is the line of the dashed line of the sea level. Perfect. Now let's look at the vector of fresh water, and see, this is the X coordinates of fresh water, and this is the Y coordinates of fresh water. So it's the coordinates are given by 5 points, 5 data points. Now let's see what is the result of this smoothing. First of all, let's do like this. Let's copy this one. Now you see what is, these are the new X coordinates for fresh water. You see that they have increased in number, X and Y. And this is because, as I said, I wanted to describe the freshwater profile with a higher resolution. And then the smoothing. And there is the smoothing, and through the smoothing, what I get is new coordinates for x and y. This is x and this is y. And the new coordinates are smoothed, made more regular. Okay, perfect. Now I have to compute h, which is given by the y coordinates of the freshwater profile with the higher resolution minus the level, the sea level, and here I am computing the h, which is given by 40, capital H is given by 40, as you remember, times lowercase h. And then I have to adjust to the altitude of the sea level. And in doing that, with this simple, very simple couple of operations, I compute the position of the interface. I'm copying it here. And then I just have to plot the interface. And here we are. So you see that it's extremely simple. The most complicated thing to understand in this exercise is the refinement of the coordinates and the smoothing. This is the only thing that is new for you. Otherwise, if you start from the coordinates of sea level, land, and fresh water, you just compute the elevation of fresh water above the sea level, and you multiply it by 40 in order to find the depth of the interface. It's very simple. Okay, so students, I think we can close here. And so, first of all, we meet again because there is the exam to make. And I am available for any clarification you may require with the modalities that I already explained to you. Just write to me an email, or if you prefer, on the Teams chat. And I just would like to thank you very much for your patience, because, you know, teaching in this mode requires some patience by the students. I hope that I made good teaching for you, and I hope in particular you could understand and follow me in the best possible way given the conditions. So I can tell you that I did my best, and I count on your understanding and your patience for trying to get the most from what we discussed together. I wonder if you have any further question while I am stopping the registration.